Okay, let's talk about the strength or the relative strength of an acid or base. So there's two factors that we look at. We look at their equilibrium constant, Ka or Kb, and then we look at the percent dissociation, right? Percent dissociation. How much of the acid or base has been dissociated into its ions. So let's look at acids first. So the strength of an acid is measured by the extent to which it forms hydronium ions in water. So here is a reaction of our acid. So HA is an acid, right? We have that hydrogen that it can donate. When it dissociates in water, it's going to form hydronium ions and its conjugate base. So the strength basically has to do with how much or to what extent are we forming hydronium ions, H3O plus ions. So if we have strong acids, right, the idea for strong acids is that they yield nearly 100% hydronium ions. So whatever concentration of that strong acid we start with, if we put it in water, the idea is that all of the acid will dissociate into hydronium ions. Whereas with weak acids, they yield much less than 100%. So we actually have more of an equilibrium between undissociated weak acid and then weak acid that dissociates into hydronium ions. So when we look at the equilibrium constants, we're usually looking at this relative to weak acids, right? Because strong acid is thought to completely or 100% dissociate. So to understand the equilibrium between the dissociated ions and the undissociated weak acid is more applicable to weak acids. So here's our equilibrium constant where we have concentration of products over reactants, right? We have the concentration of our hydronium ions times the concentration of the conjugate base of our weak acid over the concentration of our weak acid to give us Ka. So the value of Ka increases with acid strength, right? And this makes sense because as acid strength increases, that means that we have more hydronium ions forming. And if we have more hydronium ions forming, we have a higher concentration of hydronium ions. So our numerator will increase. If our numerator increases, right, our numerator is proportional to Ka. So then our Ka value will increase. So with increasing acid strength, we should see an increased value in our equilibrium constant Ka. So let's talk about the strength of bases, right? So the strength of a base is measured by the extent to which it forms hydroxide ions or OH minus. So here is a example reaction of what happens when we have a base represented as B that is put into water. It dissociates into the base's conjugate acid because it receives that proton from water. And then water forms its conjugate base OH minus. So we can measure the extent or the strength of a base based on the concentration of hydroxide ions. So just like with acids, right, strong bases yield nearly 100% hydroxide ions, right? Because it's thought that the base, when it's put into water, it will completely dissociate. That is, however, not the case for weak bases. So to get an idea of the dissociation for weak bases, we'd look at their equilibrium constant, which is represented as K sub B. K sub B. And the value of K sub B, just like with acids, the value of K sub B will increase with base strength, because as bases increase, we will have a higher concentration. As the strength of a base increases, we will have a increased concentration or amount of hydroxide ions, and this will be reflected in a higher K sub B value. So the other factor that I want to talk about is percent ionization. Percent ionization. So we can actually calculate the percent ionization at equilibrium. And again, this is applicable for weak acids and weak bases, because for strong acids and strong bases, it's thought that we get 100% ionization. So for a weak acid, the percent ionization is defined as the concentration of hydronium ions at equilibrium over the initial concentration of the weak acid times 100. Times 100. So if we have a strong acid, the percent ionization would be 100%, right? So basically, with increasing percent ionization, that corresponds to an increase in the concentration of hydronium ions at equilibrium, which corresponds to an increase in acid strength. Similarly, for bases, the percent ionization of a weak base is equal to the concentration of hydroxide ions at equilibrium over the initial concentration of that base times 100. For a strong base, we have 100% ionization. So we expect to see, with increasing base strength, a higher increasing concentration of hydroxide ions, and therefore an increase in percent ionization. So to conclude, here is a list of some common strong acids and bases that you should be familiar with. Some common strong acids and strong bases whose percent ionization, right, is thought to be 100% because it completely ionizes. And their equilibrium constant, K, right, should be 1, because essentially whatever we start with completely dissociates or ionizes into either hydronium ions if we're talking about strong acids, or hydroxide ions if we're talking about strong bases. So we'd see a Ka for strong acids of 1, or a Kb of 1 for strong bases. So taken together, or to summarize what we just went through, there's two factors. We can look at equilibrium constant, Ka or Kb, or we can look at percent ionization of hydronium ions or hydroxide ions to get a sense of the relative strength for acids and bases. We're usually talking about weak acids, right? If we just have two weak acids, we don't necessarily know which is stronger than the other, so we would look at their equilibrium constant or percent ionization.